Today we're going to be talking about comparing boiler replacements. This is a technical presentation on the various strategies and options available for upgrading commercial boilers with a focus on enhancing efficiency and reducing operational costs. We are Steam Management. We're an EPC energy efficiency contractor focusing on sustainable solutions for steam and water systems. We serve a variety of markets, basically anyone that uses steam other than possibly residential applications. Yeah, we're in all phases of the steam system, improving efficiency with various conservation opportunities. And I should said, my name is Chase Bean. You can email me there. That's how you get your PDH certificate. At the end of the presentation, once you've completed it, email me at that email address. You can also access our old webinars on the link there, as well as this one will be posted once it's completed. Okay, so we're jumping right into it. Today, our learning objectives are going to be understanding boiler efficiency, overview of different types of boilers, benefits of boiler replacements, planning and implementation, potential challenges, financing and utility rebates, and we have an example ROI calculation. So understanding boiler efficiency, first some key terms. Burner capacity is similar to, or is equivalent to max firing rate, is equivalent to input. You'll also often see that on the nameplate. It just says input, that they're talking about the burner capacity there. What's the fuel input? For natural gas, is typically given in BTUs per hour, thousands of BTUs per hour MBH, or millions of BTUs per hour MMBTU per hour. You could possibly see it as thermal kilowatts or kilowatt therms, but it's not very common. This typically given in higher heating value, not lower heating value. Lower heating value is discounted to account for water formation during combustion. If lower heating value is used to determine efficiency, you're going to get a much higher efficiency that is a little bit skewed. And you may see that in process heaters. Sometimes it will claim a LHV efficiency instead of an HHV efficiency. This is not typical for boilers. So boilers, we're talking about HHV typically. For fuel oil, the burner input is usually given in GPH, where 1 gallon of number 2 fuel oil or diesel fuel contains about 140,000 BTUs. Gross efficiency, we're talking about the efficiency of the boiler itself, fuel in versus energy out. DOE, heating capacity, is a kind of a newer term. I mean, I guess it's been around a while now, but a newer term for gross output. So those are basically interchangeable. Net efficiency listed on a boiler is accounting for radiation losses, convection losses, and some other things. It's similar to net IBR rating. I stands for input, B stands for boiler efficiency, and R stands for radiation and convection losses. And basically, to go from your net IBR to your required gross output, you use a pickup factor, which we'll talk about in a minute. Again, I got a lot of slides today. I'm going to kind of go fast, but please feel free to ask any questions you like. I just want to throw that back out there, but I am going to kind of keep it moving just because I got a lot of material in this presentation. Okay, some more terms, combustion efficiency. So here we're talking about the energy put in, the fuel in versus what's coming out of the stack. So this is a pretty good indicator of efficiency, but it does not account for any thermal losses from the boiler, any losses from blowdown, those types of things. So you're looking at fuel in versus energy lost out of the stack. AFUE is annual fuel use efficiency. It accounts for partial loading. It's very useful. Thermal efficiency is the heat absorbed by the water or steam divided by the fuel input. So you can see that a lot of these are kind of redundant. Fuel to steam efficiency is very similar. And then you have EER, energy efficiency ratio, which is kind of a standardized measure of efficiency to compare different boilers. And this is more common for smaller boilers for heating applications. Another thing to be aware of for heating applications is EDR, which is equivalent direct radiation. This is typically given in square feet of EDR. That's kind of the unit square feet of EDR. This is a radiator rating, basically. So each square foot of EDR emits 240 BTUs per hour for 215 degree steam inside and 70 degree ambient temperature. And you can find tables that will give you that heat transfer at other operating points. But basically, you can sum up all of your radiator EDRs to get a building heating load. And like I mentioned, you increase that load by what they call a pickup factor to get your gross boiler rating. And that pickup factor has decreased over time. I'm showing kind of the history of that. These are general numbers. You will see numbers that definitely vary from this. But if you have an older boiler that you're replacing, you may not want to go gross output to gross output. That's kind of the takeaway here. If they're using a pickup factor of 1.3, you may can use a pickup factor nowadays of 1.15. And so your actual gross requirement of the boiler could be lower than the existing boiler's requirement. Methods for determining boiler efficiency. So I kind of stuck to methods that I would use on a walk down or an assessment of a boiler plant. The Hydronic Institute has published standards for efficiency verification or determining efficiency, I should say. But I'm generally going to stick to these types of things. So that's one would be to use the boiler rating. So then you're looking at the nameplate ratings, which we'll give an example on the next slide, just to determine efficiency in general terms. If you have published AFUE ratings for the boilers, that's great to compare. And then you could use a flue gas analyzer. So those measurements, some analyzers will give you a combustion efficiency on the analyzer with some inputs. Or you can take those measurements and use them in your own combustion efficiency calculation. You can also use spot reading, so just writing down the measurements that you're getting in the field and putting those into a combustion efficiency calculator, which I'll show you a kind of a snippet of what mine looks like in a second. And then, of course, analyzing trend data. So as engineers, that's probably our favorite method is actually having some good trend data, several measurements, so you can kind of put that into a heat and mass balance type of relationship and really calculate how much fuel is going in over the course of a year and how much usable energy are you getting out through your steam or hot water. Here's an example of a nameplate rating. So you see there's a gross output here, a burner input here, and a net output here. So gross efficiency, you're at 80%. Net efficiency, you're at 61.8%. So to get your pickup factor, you're dividing your gross output by your net output. And so they're using a pickup factor of 1.29. I mentioned that it's common now to use 1.1 to 1.2, or at least it was on that slide. So maybe you could use a reduced gross output of 6238 MBH for your new boiler. So that's the example there. You may encounter a pickup factor higher than that. You may want to be more aggressive with your pickup factor and reduce that even further. Just something to consider. This is my combustion analysis calculator. This is just a couple of snippets here to show you an example of the input. So here you have your fuel gas constituents. this breaks them down into their different elemental components and then sends that through the combustion process and gives you your flue gas outlet or outputs. You have some other inputs here that you can take from readings or make assumptions and get a pretty good idea of your combustion efficiency for the boiler. And I also use this to do things like size economizers and things like that. But yeah, it's a good tool to have something like this. This is something I built, but there are resources out there where you can build your own. Boiler design. Okay, so now we're talking about factors that affect boiler efficiency. So boiler design, the design of the boiler, including its heat exchanger materials, shape, construction. These things all influence how effectively the heat is transferred to the water or steam. Advanced designs often incorporate features that enhance heat transfer or reduce heat loss. Combustion efficiency. This refers to how well the boiler converts fuel into heat, as we mentioned. The things that affect that are fuel type and quality. Obviously different fuel types burn differently, and that's going to affect your efficiency. Quality of the fuel is going to affect your efficiency. How much water content, how many other kind of non-combustible materials are in there. As well as like in biomass boilers and coal, you're talking about particulate matter or things that build up on the heat transfer surfaces. Anyway, these things all start to affect combustion efficiency. And then on that same note, your combustion control. So how tightly are you controlling that air to fuel ratio? How often or how properly is that being adjusted through the control system? Operation and maintenance. Regular maintenance and proper operation are, they're essential for keeping the boiler running efficiently. Condensate recovery. So obviously, from a system standpoint, returning condensate is conserving energy, but from just the boiler envelope itself, you're talking about getting more clean water into the boiler, which is resulting in less scale on the water side of the boiler, which is and less blowdown required. So improving your condensate recovery obviously improves your system efficiency, but does improve your boiler efficiency itself. Insulation, here we're talking about the actual boiler insulation to reduce the losses through the body of the boiler. Obviously piping insulation is good as well, but we're talking about improving just the boiler efficiency here. Load management. A boiler's efficiency can vary with its load. So conventional boilers running at full capacity are generally going to be more efficient than those operating below their rated capacity. So systems designed to match variable load demands without excessive cycling or operating at low load can maintain higher efficiency. Condensing boilers don't really fall suit with this. They're actually more efficient at lower loads. So when you're sizing a condensing boiler replacement, that's something to consider. Water treatment. Proper water treatment can prevent scaling and corrosion inside the boiler. Similarly, as we discussed with improving your condensate recovery, good water treatment has similar impacts. And then you have auxiliary equipment like economizers, combustion air preheaters, feed water heaters. All of these, in a sense, are just increasing your heat transfer surface area available to pull more heat out of that flue gas to improve your efficiency. Any questions on that section? Right? Seeing any, and again, you're free to put those in the chat. I think everybody's muted, but you can post questions in the chat and we'll get to those. Types of boilers, simply put, there's water versus steam. So hot water boilers are also known as hydronic boilers. And then you have steam boilers. Some boilers can be either. The most common of which I would say are cast iron boilers, fire tube boilers, or electric boilers. It's not limited to that, but those are the ones I see the most. Regarding steam boilers, so then within steam boilers, you have water tube versus fire tube. So water tube boiler is where the water flows inside of the boiler tubes. Fire tube boiler is where the flue gases flow inside of the boiler tubes. I'm not going to go through all the advantages and disadvantages. I will say that probably the most constraining factor on whether or not you select a water tube versus fire tube is your required pressure. So fire tubes are limited in their pressure. I think a common limit is like 400 pounds, 400 psi. But really, at even lower pressures than that, people start considering water tube boilers. If you think about the shape of it in a water tube boiler, your all of your water and steam is contained inside of tubes and drums. And from a pressure standpoint, it's just stronger to have it in that type of vessel. Whereas in a fire tube boiler, you have a cylindrical vessel. It's just like a big tank, and it's not really, it usually doesn't have domed ends or anything like that. It's just a cylinder full of water. And as you can imagine, like that doesn't lend itself to being pressure resistant, I guess. So that's kind of the most constraining factor between the two. Water tube type. So most coal and biomass boilers are water tube boilers. Common types of water tube boilers are a D-type boiler. I've overlaid this on the picture here so you can see this is the steam drum, this is the mud drum, and then you have all your water tubes in this shape that looks like a D. So that's why it's called a D-type boiler. There's also an O-type boiler, A-type boiler, and then M-type radiant boiler. Flex tube boilers. These are boilers where the tubes are attached to the front and rear of the boiler, but they're kind of free to move and flex. Bent tube boilers incorporate tubes that are bent or curved, often in a U shape. These are a little bit less common boilers, but just mentioning them. So within the fire tube type of boiler, probably the most common type is called a Scotch marine boiler. These were from the 19th century. They were commonly used on ships. That's the marine part of the name. And then the design originated in Scotland. So that's where you got Scotch marine. They're characterized by the horizontal cylindrical shape, and then they're fire tube type boilers. This always worked well on ships because it was compact, robust, and it tolerated the motion of the ship. So there are actually still some preserved boats that have Scotch marine boilers on them. They're just kind of relics that are being, repaired year over year. But you can actually ride on boats that still have these. But these are very common in on land applications nowadays, and they can be used for steam or hot water heating. When you talk about 2, 3, and 4 pass, that's talking about how many times the flue gas travels across the boiler. So down and back is 2 pass, and then if it goes back across is 3 pass. So that's what that's referring to. A wetback boiler is a type of boiler where the combustion chamber is surrounded on its rear end by a water jacket or a space through which water or boiler water flows. Dryback boilers have a large refractory wall in the back. So in a wetback boiler, that first pass for the flue gases is still contained in water. On a dryback boiler, it's hitting a refractory wall and then turning and going back into the fire tubes. And so you lose some efficiency there, but when you open the boiler, you can access all the tubes, so the accessibility is a little bit easier. On the dryback boilers, the back door is generally going to be heavier because it's full of refractory, a little bit harder to remove, where the wetback boilers, it's usually like more looks like a plate or a set of plates that could be removed by hand. So there's just some differences there, but Those are the two types. You also have vertical fire tube boilers, which are just arranged in a vertical shell. These are going to be used where space is limited. And then there's other types like Lancashire boilers, horizontal return tubular boilers, and Cornish boilers. Did notice a question. The pickup factor. So Bob says the pickup factor, is that for when a building goes into morning warm up, when piping and terminal heating equipment in the building is cold and creates a greater load on the boiler? If yes, then wouldn't peak heating load for a ventilated building include both envelope and ventilation load? And wouldn't good practice include keeping ventilation systems off when the building goes into morning warm up mode? What I'm getting at here is that with the ventilation systems off during morning warm up, wouldn't that effectively reduce the load significantly enough to negate any need to factor in a pickup factor? I know that it's used for that, as far as like it's basically just a margin, right? So if you have considerations like that, then you can select a higher pickup factor. However, it is also accounting for losses within the piping system. And your losses to your pipe are generally going to be around 10% of your energy. So when you put on, if you go from bare pipe to an insulated pipe, you're going to save around 90% of the energy that would normally be lost. So you're going to lose, you're still losing that 10%. I guess it's not 10% of your energy, but it's 10% of, you're still losing 10% of what would be lost from a bare pipe. But anyway, you're losing it through that. You're losing it through system leaks, through traps, cycling, all these things. So it's not just for the morning warm up. It's just for all of the system losses, and it's like a simplified way to just add some margin to account for those losses. So I guess my answer there would be, if you're eliminating the warm up factor of it, then you would just use a lower pickup factor. And I don't know what I would recommend there, but I don't think that you want to go any lower than like 1.1 for system losses. That would be a pretty aggressive pickup factor, unless you already have margin in your building load calculation.
Hey Chase, there's one more question in the chat.
Oh, okay. Oh yeah, go up a little bit. Does a steam boiler efficiency improve at partial load conditions when a condensing stack economizer is installed as a retrofit? That's a good question. I would think that it would. One of the things that boilers sometimes don't do at partial loads well is maintain their combustion efficiency. So your air to fuel ratios can get off a little bit, but with modern controls, that's really been tightened up a lot. I don't know. I would think that it would, like a condensing boiler. I would think that it would operate the same, but I'm not sure about that. That's a good question. Thanks, Cody. Next type of boiler, cast iron boilers. So these are usually, you're going to see the sectional kind. There's horizontal and vertical sections. The most common is the horizontal sectional type. And these are field erected. Typically, they're made from individual cast iron sections, which are bolted or welded together during the installation. They're common for residential and light commercial applications due to their durability and heat inertia properties. And they're common for hot water or steam applications. So you'll see on their nameplate that they'll have ratings for steam output and water output. I don't know if you can see it on here. I didn't post this picture for this reason, but you can see it. This picture is on here. I just wanted to give a tidbit that when you look at these in the field, they give the nameplate often has a rating for all the like how many sections you have. There's a different rating for each number of sections. And they will usually just mark how many that unit has. So sometimes it's hard to tell just looking at it how many sections there are because the sections are covered with the boiler jacket. But they will usually mark it. So that's how I usually can tell. I got another comment in here. Boiler efficiency when drawing the box around the boiler plus condensing economizer would increase at all load conditions, but the condensing economizer is generally most efficient at max boiler load and max process steam load. Okay. All right. So it's not more efficient at partial loads, Adam is saying. Were these types of boilers once called pork chop section boilers? I don't know that term. That sounds reasonable. That may be true. I didn't know that term. Okay, so then you have non-sectional or monolithic cast iron boilers. Those are I've never seen one of those, but apparently they exist where they it's just a cast iron boiler in one piece. And then we come to condensing boilers. So what is a condensing boiler? I think the thing to understand here is that the flue gas is the flue gas dew point, and that's where constituents start to condense out of the flue gas. So one product of combustion of the combustion reaction is water. In a conventional boiler, the water in the flue gas remains in its vapor form, but in a condensing boiler, the additional heat removed from the flue gas results in condensation in the flue gas. And so it will remove heat down through just basically extra surface area until the flue gas gets to what's called its flue gas dew point, and that's when the water starts to drop out. And so when that occurs, you get additional latent heat capture from that phase transformation, as well as getting some additional sensible heat captured because you're enabling a lower flue gas exit temperature. And so that's what's going on here. So we have our combustion air in, it's going across, there's a burner here firing. Those products of combustion are heating this primary heat exchanger. And on a conventional boiler, not that this is an accurate diagram of how a conventional boiler looks, but conceptually on a conventional boiler, you would exit at this point. The flue gases would go up the stack. On a condensing boiler, they continue on into this secondary heat exchanger section where water starts dripping out of the flue gas, and the rest of the flue gases escape out of the stack as normal. One thing to note here is one thing that really enables condensing boilers to work is a cold water, or at least many of the condensing boilers, is a cold water inlet temperature. So it's a standard recommendation is for this temperature, this return temperature to be below 130 degrees, so that this heat exchanger is actually dropping the flue gas temperature down low enough to capture that additional capacity. So in a conventional boiler, you're getting 80 to 85% efficiency is typical. It can be pushed higher, but that's kind of a typical range. It's also frequently lower. But in a condensing boiler, you're going to get 94 to 98% efficiency if if you're able to get that condensate out of the flue gas. This is just something to note. People talk about category 1, category 2, etc. This is what they're talking about. So you have non-condensing boiler categories 1 and 3, and then condensing categories 2 and 4. The major takeaway here from a replacement standpoint is that these require different duct materials, and so you can't take a chimney from a conventional boiler and reuse that for a condensing boiler. It's not, the materials are not suitable. And so there are liners that can be installed to accommodate condensing boilers, but more often than not, you're just going to route a new duct out for that's appropriate for the service. Other types of boilers, just mentioning hybrid boilers. So here I'm talking about a combination of water tube and fire tube sections, combined cycle boilers like heat recovery steam generator on the back of a combustion turbine, waste heat recovery boilers. That's if you had a really hot waste heat stream, most likely in a large industrial facility, which is hot enough to generate steam. You could just have it's basically like a heat exchanger boiler to generate steam. And then we have electric boilers, which are coming up more and more. I've evaluated these for a few clients. So far, the operating cost and the initial install cost outweigh the benefit, but they are going to start having I'm predicting they're going to start having a bigger place in the world as we move towards decarbonization. How do you measure the combustion efficiency of the condensing boiler? I think it's still the same kind of method. Um, there's definitely testing procedures to do that. If I was doing it or I was trying to estimate it, I'm still looking at flue gas temperatures and kind of what I described before. So your flue gas temperature is going to get much lower, and then you're going to have to calculate how much of that is water and how much latent heat is being taken out of that as well. Adam asked, how is corrosion in the boiler typically mitigated in a condensing boiler when incoming feed water is cold, so dissolved oxygen is generally high? That is a good question, because a lot of these boilers are for heating applications. You're usually not using a particularly sophisticated water treatment system. We are talking about water boilers in most cases. So the scale that results from steam generation leaving those constituents behind is more significant than a water condensing boiler. But yeah, that's a good question. I'd have to research to give you a better answer on that. Types of boilers, considerations for selecting the right type of boiler. So you're going to look at your heating, steam, hot water load requirements, load profile, fuel type, boiler efficiency, power requirements. This is kind of straightforward with package boilers, but if you're looking at a larger biomass boiler, coal boiler, there's actually a lot more motors involved, and so the power requirements are significant. And then you have system design and integration, maintenance and serviceability. These all affect your decisions for selecting a new boiler. Terrence posted the pork chop boiler, so that's a fun term, I guess. Yeah, it looks like a cast iron section, like metal radiators. I don't know. I have to look that up. That's interesting. But yeah, if it's made out of cast iron and they're assembled together, it would be considered like a cast iron sectional boiler, I'm sure. So yeah, thanks, Terrence. Other considerations, space availability, accessibility. I mentioned the cast iron boilers. That's a big thing. If you have a cast iron boiler, a lot of times those boiler rooms, maybe they just have a stairway or something to access the room. And when you go look at a completely assembled package boiler, which most of the condensing boilers are going to be, you may have trouble getting that into the space. As well as, a conventional boiler if it's not a sectional field assembled boiler. On those cast iron boilers, you can actually just take those sections into the room like with a hand truck. I mean, they're just sections that can be handled by hand, and you can access tighter spaces. So that's something to consider, is if you have a lot of architectural structural modifications required to get in the space, that can really kill the return on investment on the project. Piping and ductwork compatibility. We talked a little bit about the duct aspect of that, code compliance, integration with building systems, environmental compliance, feed water supply, what type of feed water you're using, what type of makeup water you're using. Adam mentioned concerns with scale and things like that. So yeah, those are all considerations. And then you got budget and life cycle costs, safety and reliability, and then future expansion and flexibility. So again, not pushing condensing boilers per se, but when you are considering a condensing boiler, you're often putting in, you're often replacing 1 or 2 boilers with 2 to 6 boilers. And so how much room do you have left to expand that further? How flexible is that system? Are you operating at full load where you're not really getting the benefit of the condensing boiler at some point? So those are all considerations. Any more questions on that section? We do have a poll here. So you can manually enter that response and it'll pop up. All right, I'll keep moving while you guys are answering that. Boiler yearly operating costs. So this is kind of a simple pie chart for maybe a packaged boiler's operating costs. The takeaway here is that the fuel portion of this is, 45% of your operating costs. This is a significant cost. So efficiency obviously has a big impact on your operating costs. And then indirectly has impacts on some of these other sections like repair, other services like outside services coming in. All of those can be mitigated somewhat by operating more efficiently or installing a more efficient boiler. Financial benefits. Again, we discussed reduced fuel costs, lower maintenance costs. There's energy rebates and incentives available for these projects. You have avoided carbon tax penalties, like in the case of, say, putting in an electric boiler. If you have carbon taxes, but not those same taxes on your electrical supply, then you're avoiding carbon tax penalties. Extended equipment life, and so on. Environmental benefits. You have compliance with new environmental regulations, improves environmental reputation. You're hitting maybe corporate sustainability goals or helping hit those goals. So that's certainly a big driver nowadays for these types of projects. And then you have safety. So you have with newer boilers, you can get improved system reliability, improved safety. Like I said, efficient boilers are going to operate in a way with tighter air and fuel controls and all. You're going to mitigate some of the things that have caused, like the buildup and things that have caused tube failures on boilers before, which leads to boiler failures and boiler explosions and things like that. So not saying that old boilers are all unsafe if you're properly maintaining them and everything, but you can get an aspect of safety improvement here with a new boiler. I have another poll here. When considering a boiler replacement at your facility, what are your top priorities? No right or wrong answers here, just your opinions. Now we'll kind of go through planning and implementation. This is just kind of a high level thing to just kind of think through the steps of it. So assessment and planning. First, you're going to have your site walk down. So you and your preferred contractor perform a walk down the site to assess, existing boiler conditions, piping conditions, condensate water return temperatures, flue gas configuration, location accessibility. Like I mentioned, how are you going to get the new boiler in, get the old boiler out? You can generally cut the old boiler up, so that's not as big of a concern. But how are you going to get the new boiler in? Combustion air, how many vents and louvers are there, and what's the combustion air availability? Water treatment, makeup water source, what are the concerns with that, and et cetera, et cetera. There's a lot of things to check. And then you're going to select a new boiler. So you have equipment sizings and specification. You're going to go out to bid. You're going to select the preferred manufacturer, and you're ultimately going to purchase the boiler. Depending on the complexity of the project, you're going to work a lot with your boiler manufacturer to, on getting submittals and things and kind of collaborating on the design especially if it's a more complicated project and not just a small heating boiler. And then at some point, you're going to hire professionals, right? Like you're going to engage qualified contractors for project development, and then eventually hire, hopefully, the same contractors for the installation. Then you're going to obtain necessary permits, verify codes and standards requirements. Here's a partial list here. These are not all permits that you have to gather. They're just different applicable codes. But there's a lot to consider here to make sure you're complying with the standard codes. Engineering. So I won't go through the whole list, but all the engineering deliverables required to pull off the project. This can vary dramatically from how complex the project is, how engineered like if it's a much larger boiler, then there's going to be a lot more engineering deliverables and a lot more engineering hours in the project than, say, a heating boiler. But it is certainly a big aspect of the project. Removal of the old boiler. You're going to disconnect. This is kind of simplified, but you're going to disconnect the utilities, demo, and remove the boiler, and then install the new boiler. You're going to prepare the site, install the new boiler, install auxiliary equipment. And then you're going to commission the boiler. Initial testing and light off, pipe flushing, all that good stuff, system commissioning, safety checks, and then documentation and registration. So you're going to revise your drawings for, or your contractor is, revise the drawings for as-built. Make sure you have all your documentation in place for your warranties and guarantees, and make sure you're submitting everything for compliance with building regulations, and for your boiler inspector, and have him out to inspect the installation. Close out, instruction and turnover. Basically, you're going to educate the site operators. You're going to submit a turnover package, or at least operating manuals and things. I always refer to that as a turnover package. And then you're going to, as the end user, you're going to plan for maintenance, and even if you outsource that. Potential challenges. So in general, this is just a simple list here, but you got your costs. So you have initial investment costs and hidden costs that can come up in the project. Sizing and selection. You got to get proper sizing of the boiler, select the proper type of boiler for the application. Then you have installation challenges, complexity, downtime that's required for the installation. Regulatory and compliance issues. So meeting those building codes and regulations, getting all your permits, environmental considerations as far as energy efficiency, carbon footprint, emission standards, compatibility, finding the right professionals. We'll talk about condensing boilers in a second, but this is just kind of general. And then you have maintenance and warranty concerns. So making sure that you're covered there with the right selection of a manufacturer. With condensing boilers, there's more issues with system compatibility, from existing infrastructure, water temperature. We talked about the flue duct compatibility is not there. You have to account for the condensate drainage. These are usually packaged units. They're not field assembled units, so there's space and accessibility considerations. They may have a higher upfront cost and potential structural modifications, especially if you're, say, replacing one boiler with several boilers, or if you need to have structural modifications to get the boiler into the space. And then you have regulatory and compliance issues, performance expectations. You got to make sure that your process, that your process is actually going to perform in a way to really get the benefit of the condensing boiler. Like we mentioned, if you don't have a low enough hot water return temperature, you're not going to get the full benefit of that condensate in the flue gas. One thing to note there, if you're familiar with primary, secondary variable configurations on the hot water system, usually you have a constantly flowing primary loop, and then the secondary loop pulls some water off of that to send it out to the building loads or the process loads or whatever. This is usually for a heating application. When you think about the return temperature being low, if you have that primary loop, you are blending some portion of that loop with the return water. So you are actually taking water out of the outlet of the boiler and mixing it right back with the return water. And so you're not getting the full temperature drop coming back to the boiler. So it may be pertinent to rearrange the configuration to where you're in a primary variable configuration so that you can go out to the users and come back at a lower temperature into the boiler and get the right performance out of that. Any questions there for planning and implementation? We have another poll here. What do you see as the biggest challenges for boiler replacements? Cost, selection, regulatory and compliance issues, compatibility, installation challenges, finding the right professionals. Yeah, so the responses in there. If you do have any questions, happy to go through those. We're getting close to the hour, so I'll keep going here. Financing and utility rebates. So just so you're aware of the different funding options, obviously have business loans like traditional bank loans for capital equipment, equipment financing. This is specifically for purchasing business equipment. And then leasing, you can opt to lease a boiler instead of purchasing it outright, or even some companies go for a long time where they're renting boilers, like mobile boilers. And they have mobile boiler feed water systems, so you can rent a lot of boiler equipment. It's not usually the best option financially unless you just have a temporary situation. Energy efficiency loans. So some financial institutions will offer favorable terms for projects that improve energy efficiency, government grants and incentives, on-bill financing for the utility. So you can get a loan from the utility and then you pay that on your utility bill. Utilities offer some utilities offer interest rate buy downs as like an additional incentive. So you get your incentives for the project and then they will buy down the interest rate of a loan so that you can get a 0% or very low percent rate on the project. Then there's PACE financing and internal financing, which is like just using your capital equipment budget to purchase a boiler, basically. And then another big one here is ESCOs. So we have some ESCO professionals on the call, I think, today, but not a but. This is a good option for funding projects like these. Generally going to be packaged with other projects as one big contract. They have different forms of contracts, so we'll kind of go through these quickly. Energy performance contracts is where the ESCO implements energy saving measures and guarantees the savings will cover the project costs over the contract term. So if the savings aren't achieved, the ESCO compensates the client for the shortfall, and these are best for clients looking for guaranteed savings without the upfront investments. Guaranteed contracts are similar to EPC, but the client secures the financing. The ESCO still guarantees the savings, and it's best for clients that want to secure their own financing but want guaranteed savings. Shared saving contract description. Shared saving contracts is where the ESCO finances the project. The cost savings are generated or split between the client and the ESCO, and it's usually determined by or predetermined, like what percentage, what the split is. And then the clients, it's best for clients who will wish to avoid upfront cost, but are willing to share the savings with the ESCO. Energy supply contracts is when the ESCO provides energy at a lower cost than the client's current rates, often by installing more efficient equipment or utilizing renewable energy resources or energy sources. This is best for clients looking to reduce their energy supply costs and dependency on the traditional energy sources. You have managed energy service agreements, similar to energy service agreements, where the ESCO assumes responsibility for a client's energy infrastructure, including the operation, maintenance, and upgrades. The client pays a service fee, which is less than their historical energy costs, allowing savings to be generated over time. So this is for clients kind of looking for the ESCO to come in and manage their facility, but still get a positive cash flow out of it. Power purchase agreement is specifically generally for renewable energy projects, so it doesn't necessarily apply here as much. But then energy as a service is something that I've seen some where it's almost, it might be called steam as a service, but that's the build, own, operate, and maintain model, where the ESCO would basically install a boiler plant, and then you would pay for that steam as you use it. And that can also be arranged for other companies outside of ESCOs. Anyway, those are just some funding options. All good options and all have their place depending on the situation. Boiler replacement incentives available, so utility rebates and incentives available. These always, as always, vary by utility and even between service areas of the same utility, or maybe not even between different markets in the same utility. They can be complicated to navigate, but they obviously represent a significant financial tool to help on the return on investment of the projects. We can provide the study evaluating the conservation opportunity and work with the utilities to determine what the rebates would be and to work through the administration of those rebates. The rebates that are actually available are going to be for the engineering study. This is generally speaking. You can't just say that this is the same for all utilities in all situations, but this is kind of in general. There may be an incentive available for the engineering study. These are often tied to a stipulation that the measure is implemented, so that you do have to move forward with a boiler replacement project to get the incentive. Prescriptive rebates are available for these, but that's particularly for small boilers. For larger boilers, it's going to be a custom rebate. $1 to $6 per therm is typical. Oftentimes these will cap out, but yeah, usually get savings on a therm basis. And the utility usually has an engineering team. I would say always has an engineering team for their incentives that will kind of help you work through what it would actually be credited for the project. Any questions there? Just planning and implementation. And then I'll keep moving so we get through this example. This is a simple ROI calculation. We're talking about going from a cast iron boiler to a condensing water boiler. So first you're going to determine the existing boiler efficiency. I'm just using the nameplate data like we talked about. You have an input of 6134, an output of 4940, and that's giving you an 80.6% efficiency. For the condensing boiler, first we're going to calculate our fuel expense based on that. We're going to say it's at 65% load. This is the fuel cost is $10 per million BTU or $1 per therm. And you're going to have a $203,342 fuel expense. To get so basically what you want to do is use your new efficiency of your condensing boiler at 95% to get a new firing rate. Use that times the boiler load or average load, and then get a new fuel expense. And that is basically your savings. So you're going to about a $31,000 savings there from your original to your new. Turnkey project cost of $300,000 and a possible incentive of about $124,000. I think this would probably in most utilities be capped out before this, but take that as it were. And this is your net initial investment, and this is your simple payback, 5.7 years. So that's just kind of a simple example of the potential for energy savings. This isn't accounting for any electrical savings that may be attained with a VFD or a smaller combustion air fan. You know, you have maintenance savings, you have other savings that could be, you have avoided equipment replacement cost savings down the line, because maybe if you're even looking at this project, you're already having to replace this boiler. So you might as well get a more efficient boiler that's going to help pay for itself after some time. So, you know, these can be appealing projects. I don't think you would go in and replace a boiler that's, you know, 5 years old. But if your boiler's getting up there in age, you know, there is a payback. There's a pretty good payback here, particularly in some of the contract models where they can do kind of longer terms. And that is it. So thank you guys for attending, guys and gals for attending. Any questions? I'd love to hear them now, or you can email me questions. Again, if you would like a PDH certificate, you can email me there, and I or Ashley will get that back to you pretty quickly. We will keep an eye out for emails about our next webinar. We'd love to have you back. And we, you know, obviously, if you have any applications that we can help you with, we'd love to jump on a call about that as well. But yeah, thanks everybody for attending. I will hang out for a few more minutes and answer questions that come up. We have a poll there, so kind of help us with some feedback on what you guys want to hear about. And thanks. Oh, we got a question here. Is biogas typically compatible with natural gas boilers? What type of physical or controls modifications need to be made? So I actually used to work for a company that made gas blenders to basically generate synthetic natural gas. We kind of focused on propane, but I know that they are now using the same technology to blend biogases with air. So when you talk about gas blending for combustion, you're talking about matching. I guess in kind of simplified terms, you're talking about matching the Wabi index of the gas. So you can take like propane and mix it with air and create what's called synthetic natural gas. So people use that as backup gas, but they use the same technology to blend biogas so that it's more consistent for the burner. So anyway, Cody, you can I can share with you more info on that, like what equipment I would recommend for that. But yeah, it's a good question. Yeah, thanks everybody. Appreciate it. I will stay on for a few more minutes. Thanks everybody for attending.